All right, another thrilling installment of our lecture series. We're up to lecture 14 of 95. We're going to look at some prior knowledge for this, which is, so firstly, we're going to look at reciprocal circular functions, and some prior knowledge for that is regular old circular functions, which we spoke about in lecture 1. So I'll put that link below. Some of the key concepts we're going to cover in this are what's called the cosecant function, the secant function, the cotangent function, and then we'll look at the Pythagorean identity for reciprocal circular functions. As always, if you're finding these videos at all useful, please consider liking and subscribing so we can get this out to as many people as possible and help them understand, these interesting concepts. So let's jump into it. We're going to look at the cosecant function first. And here it is. And I reckon this looks like a piece of art in itself. I think it looks very interesting, and what our job is to try and understand it. So first, let's begin with this idea of a reciprocal circular function. A reciprocal circular function is basically 1 over our regular circular functions, those being sine, cosine, and tan, right? So our first one here is what's called the cosecant function, and that's basically 1 over sine of x. So it's the reciprocal of sine of x. And then there's all these interesting properties we can say about it. So let's maybe just look at it to begin with. In green, we have the cosecant function. Okay. In red, I hope you recognize we have the sine function. Okay. And what you'll notice is you start getting asymptotes. And I think this is a good place to start. So let's think about what's happening. As sine of some value goes to zero, well, for example, we know that sine of pi goes to zero. So 1 over something that's going close to zero is going to get very large. So we can see that for the cosecant function, we get vertical asymptotes wherever sine goes to zero. And sine goes to zero at integer multiples of pi. So at pi, 2 pi, 3 pi, 4 pi, and negative pi, negative 2 pi, negative 3 pi, and so on. So again, just to really drive that point home, we're just taking 1 over our sine values for any given x value. So let's imagine now that our x value is pi on 2. Sine of pi on 2 is 1. 1 divided by 1 is 1. So you'll recognize, hopefully, that you're going to get a point of intersection at pi on 2 because the reciprocal of 1 is just itself. So you end up getting an intersection there. I just realized as well that I haven't drawn the asymptote on the y-axis, but I think you would agree that there would be a vertical asymptote at x equals 0 as well, because sine goes to 0 at x equals 0. Yes. Okay. Let's look at the domain then. So just based on this idea of vertical asymptotes being at integer multiples of pi, the domain is going to be all real numbers, not including integer multiples of pi. Okay, thinking about the range can be a little bit more tricky, but let's for a moment think about the range of sine. So the range of sine clearly goes from -1 as a minimum to +1 as a maximum. Okay, when we take the reciprocal of that, we're taking 1 over those values in that interval. So the values in that interval are going to be proper fractions. That's one way to think about it. So for example, the number -1/2 would be in that interval. So if we took 1 divided by -1/2, we're actually going to get -2. So essentially what we're doing is we're taking 1 over proper fractions, which gives us values outside. We can't possibly get values inside the interval -1 and 1. So the range is going to be all real numbers excluding values that are in the interval -1 and 1. And this can be a little bit confusing. We're excluding values that don't include -1 and 1. So we can see what that means is that the cosecant function can include the value at the point 1. And that's why we can see that point here does include the value 1. Because, when you take 1 over 1, so let me explain. 1 is a valid output of the sine graph. So 1 divided by 1 is fine. You get a value of 1 on your cosecant graph. Okay, and similarly, turning points, you're going to get turning points halfway between your asymptotes. So you're going to get them at the odd multiples of pi on 2. So you're going to get them at 2n plus 1 pi on 2. Remember this, when you see 2n plus 1, you need to think that's giving us all the odd numbers. So you get a turning point at 1 pi on 2, 3 pi on 2, 5 pi on 2, 7 pi on 2, 9 pi on 2, and obviously in the negative direction as well. So that is your x coordinate for all your um, turning points of the cosecant function. Okay, hopefully that's a pretty good overview of the cosecant function. If you can wrap your head around that, the secant function is very similar. So let's go and have a look at that. And this is what it looks like. This is the secant function. So in the same way that the cosecant function is defined as 1 on sine x, the secant function is defined as 1 over cos x. And things have basically just been shifted. In fact, I'll just show you that. If we shift the secant function pi on 2 units to the right, you'll notice that this is just the graph that we had before. So there's strong similarities, obviously, between these two functions. Just like sine and cosine are phase shifts of one another, cosecant and secant are also phase shifts of one another. In any case, let's just leave it as the secant function here, which is obviously in green. And again, I think a good place to start is with the vertical asymptotes. This time, we're taking 1 over cos. So we're going to get vertical asymptotes where cosine goes to 0. Now, cosine goes to 0 at pi on 2, 3 pi on 2, 5 pi on 2, if you think about your unit circle there. So you're going to get vertical asymptotes at odd multiples of pi on 2. And that's what you can see we have here. You've got a pi on 2, 3 pi on 2, 5 pi on 2, 7 pi on 2, and so on. Okay, and so using that same logic, the domain is going to be all real numbers not including the odd multiples of pi on 2. Okay, similarly, the turning points are going to be halfway between that, okay, because cosine goes to a maximum or a minimum at integer multiples of pi. So you're going to get turning points at n pi. Yeah, you're going to get turning points at n pi. So here we go. At negative pi, we get a turning point. At negative 2 pi, we get a turning point, and so on. And similarly, for the exact same reasoning as before with the cosecant function, the range of the secant function will be between -1, will be all real numbers not including -1 to 1, but you can include -1 and 1 themselves for the same reasoning as just before. So yeah, I think that's pretty interesting. And obviously, again, they are phase shifts of one another, which I think is pretty cool. All right, let's look at the last reciprocal circular function, which is the cotangent function. And this one's interesting, I think. Okay, so just take a step back for a moment and think about the tangent function. The tangent function is sine x over cos x. So the cotangent function is going to be the reciprocal of that. So cotangent is going to be cos x over sine x. And as you can see here, this is the graph of the cotangent function. And you might notice it looks a lot like tan, but it's actually been reflected in the y-axis and shifted to the right a little bit. And there is obviously very sound reasoning for why that occurs. And here's the reasoning here. So let's just talk through it. So using the definition of trigonometric functions, we have that cos x, we have that tan x equals, sorry, we have that cotan of x equals cos x over sine x, just the reciprocal of the tangent function. Okay, then we're going to use some complementary properties of sine and cosine. So just recall that cosine of x is sine of pi on 2 minus x. And I encourage you to go to Desmos or GeoGebra and check that that's true. But basically, if you reflect sine of x in the y-axis and then shift it all to the right by pi on 2, you just get cosine of x. And similarly, here, if you reflect cosine of x in the y-axis and shift it pi on 2 to the right, you get sine of x. So that's a very interesting sort of symmetry property of cos x and sine x. And we're actually going to use that to show what the cotangent function can also be equal to. So what we do is we take this and substitute in these properties. So we get cos x on sine x equals sine of pi on 2 minus x over cos of pi on 2 minus x. Okay, and then what we need to do is just recognize that we've got sine over cos, numerator and denominator, and we've got the same thing in the brackets. So that must be the same thing as tan of pi on 2 minus x. And so what we can say is the cotangent of x, aka cos x on sine x, is equal to tan of pi on 2 minus x. And so, yeah, that is it. The cotangent of x is basically um, the tangent function reflected in the y-axis and shifted pi on 2 to the right. So I think that's an interesting result. And, what I'll do is I'll just show you that. You can sort of see that it's here. Tan looks like that, doesn't it? But in fact, you just got to recall that tan would actually go this way. So you can see that there's been a reflection in the y-axis and it's been shifted pi on 2 to the right. So this is the cotangent function. If we were to if you would sort of if you had tan here, let's say let's think that we're at tan of x at the moment. We're at tan of negative x at the moment, and then if we shift that pi on 2 to the right, we get the cotangent function, which looks like that. Hopefully that's making some sense. Okay. The domain then we can think about is, again, where do we get our asymptotes? Remember, cotangent is sine of x. So basically you're going to get asymptotes wherever the denominator goes to 0, and the denominator is sine x. Sine x goes to 0 at integer multiples of pi. So you're going to be at 0, pi, 2 pi, 3 pi, 4 pi, and so on. So your domain is going to be all real numbers, not including integer multiples of pi. The range is easy for this one. The range is just all real numbers. And your vertical asymptotes, as we said, are just at integer multiples of pi. So that is the cotangent function. So I think that one's interesting. Yeah, that's what it looks like. Let's have a look at the last thing we're going to talk about, which is the Pythagorean identity. And hopefully you can recall from previous learning about regular circular functions that cos squared x plus sine squared x equals 1. That is the Pythagorean identity. That hopefully isn't news to you. But what we can do is we can incorporate some new information now that we've learnt about reciprocal circular functions. I hope you'd agree that it follows that if we divided everything here by cos squared x, we would get cos squared x divided by cos squared x, which is 1, sine squared x divided by cos squared x, which is tan squared x, and 1 divided by cos squared x. Well, we just learned that 1 divided by cos x is the secant of x. So 1 over cos squared x is the secant squared of x. So it follows that 1 plus tan squared x equals the secant squared of x, provided that when you divide by cos x isn't equal to 0 because that's in the denominator, yeah? Okay, I encourage you to think about this second property here. This is the same thing, but we just divide everything by sine squared x. Okay, CSC is the cosecant of x. That's another way to write it. How did I write it before? I wrote it before as COSEC, but you can abbreviate it to CSC, which is probably better. Okay, let's just talk about what's going on here. Hopefully you can recall from just regular circular functions that this point here on the unit circle is defined as the coordinate cos of x, sine of x, cos x, sine x, xy. And then I think you would recall, hopefully, that this length here is tan of x. Okay, so using this property, which we just spoke about where it came from, just visually, we could sort of say that, all right, we know that this is a unit circle, and we know Pythagoras' theorem, a squared plus b squared equals c squared. So 1 squared plus tan squared equals this length here. But we know that that must be the secant squared of x. So on our unit circle, it's actually this length from the origin up to this point here, that represents the secant of x. And we can see that that obviously holds for these right angle triangles we create on the unit circle. So now, hopefully you've got a visual idea of what length the secant of x represents and why this Pythagorean identity holds true for that property. Okay, hopefully that was somewhat useful. And yeah, let me know if you've got any questions and looking forward to hearing how it's all going. So talk to you soon.